Hello, and welcome to Aggressive Physics. Today is day 107, and what I'd like to discuss today is the graphical representation of electric fields. Now, the electric field, as we defined before, is the region around a charged object in which other charged particles will interact. There'll be forces acting on those objects, and it's defined mathematically as the force per unit charge. Now, today we'll look at a way to look at it visually. Much as many of the other topics we've done in this course, we have a mathematical approach and a graphical approach. We did that with vectors, we did that with motion, we did that with even projectiles. In fact, a visual representation will often allow us a way to solve a problem more rapidly than plugging numbers into equations. It also gives us a good view of how multiple objects will interact without having to calculate many different answers at different locations. Now, in terms of the electric fields, I want to discuss some typical values that we may be dealing with because it's not something that we're familiar with like gravity. Now, for example, a fluorescent light bulb will exert an electric field around it of around 10 newtons per coulomb. On the other hand, the atmosphere during clear weather where there's no storms is about 100 newtons per coulomb. On the other hand, if there's a lightning bolt around, that may produce an electric field around 10,000 newtons per coulomb. If we take it to a much smaller scale, an electron in a hydrogen atom will experience an electric field of around 5.1 times 10 to the 11 newtons per coulomb. So the range of values for the electric field varies greatly depending upon the situation involved. Now, if we look at a visual representation, what that will do will give us a way to look at an electric field with a pictorial view. Now, basically what we're going to do is draw field lines to represent the electric field. And it's drawn to show the direction a force will be applied to an object in the field. And we always use the positive test charge just like we did mathematically. So it will always be what direction will a positive test charge move within the field. Those are called field lines when we draw them. Basically, if we have a situation where the field lines are drawn, we'll be able to tell where the field is strongest, where there may be some strange anomaly of the field line, and it may be just easy to tell where it's going to be strong or weak. This reminds me a lot of a topographical map and contour lines. In a topographical map where the contour lines are close together, that represented a steep grade. Where they're spread apart, it's more of a shallow grade or almost flat. So the same thing applies with an electric field. If we think about the rules for drawing the electric fields, we always start at a positive charge and end at a negative charge because a proton will move away from a positive charge and towards a negative. The number of lines is directly proportional to the strength of the field. So if we had two identical spheres and we were just trying to find the field around them, a stronger field would have more field lines than a weaker field. The closer the line is to one another, so as the lines are closer, just like in a topographical map, that would represent a stronger section of the field. And also, we need to realize that field lines will never cross. You can't have more than one value at any point. Just like you can't have two elevations in a topographical map, you can't have two places on an electric field that share the same value. Now, in terms of drawing the fields, we could have a single point source, and that would be a series of lines emanating from the center outward. Now, what's interesting to note on these is that you'll never have a field line within the sphere. So if you have an electric field of a Van de Graaff generator, it will always start at the surface of the Van de Graaff and emanate outward. If it's a positive source, it would emanate away. If it's a negative source, it would emanate towards. So this is very similar to a gravitational field, except that in some cases an electric field can be repulsive. Gravitational fields would always be directed towards the center of the object. Now, if we have two unlike sources, we have a situation where we pushed away from the positive source and moved towards the negative. And what it ends up creating is a pattern where you have stronger lines because they're closer together near the two charged objects themselves, and in between them it's fairly strong, and the field is weaker as you go farther away. And the field is shown in the slide that you're looking at now. Additionally, you could have a situation where you have two fields that are created from the same charge sign. So in this case, I have two positive charges, and they happen to be equal. What that is going to create is a field that opposes one another in the center. It pushes apart. And you end up having a spot where there's really no field present at all, and that's at an asymptote in between the center. So the asymptotic line would go vertically in this case, and we usually denote it with a dotted line. Now that asymptote will be directly in the center if they have the same charge. Now if one of the sources is stronger than the other, that's going to push the asymptote towards the weaker one. So the stronger one will have, I guess, a stronger effect on particles within the middle of the two objects themselves. So you have an asymptote that is created when you have like charges and you have a field between the two. Some examples of some real electric fields are shown in this slide, and it shows the difference between two like sources and an unlike pair of sources themselves. Now additionally, we may have a parallel plate, and in between that we have a very specific type of electric field. So if we have two long lines that are both charged, the field in between them is uniform. And the way we can denote that is you can see that the lines are equidistant. They're parallel to one another. Now remember, if you have lines closer together, they're stronger, and if they're farther apart, they're weaker. So if a field is parallel, that shows that the field is uniform throughout. If we're doing any experimentation with electric fields in the lab, we'll use parallel plates to understand what the field does because it has a nice uniform view. Now, you will notice that on this diagram you have curved lines at the end, and that's called the fringe effect. When you get close to the edges of the parallel plates, it will act like two unlike sources, and you'll start to see a curved pattern. So if we're going to use this in lab and we want to have a uniform field, what we're going to want to do is try to put the objects that we're analyzing as close to the center of the parallel plates as possible. Towards the ends, it is not as uniform as it is in the center. So we want to stick to the center so we have a nice, even, constant electric field. Now once again, here are some other electric fields that you can see. These are for oddly shaped situations. What you could do if you want to find the value of an electric field at many different spots, you could actually map it out doing it mathematically. But once again, a visual representation will allow us to answer questions quickly because we can look at the picture and just see where are the lines bunched. If they're bunched, it's strong. Where are they spread out? If it's spread out, it's weaker. We could also tell exactly what direction a charged particle will move because it's going to move along the field lines themselves. So it's going to move in the direction of the field line. If it happens to be a negative charge, it will move in the opposite direction of the field lines because we always denote the field lines as what would happen when we put a proton in the field. WWPD. What would a proton do? Now, as I stated earlier, the electric field inside of a conductor is zero. And that's because the charges are really distributed on the surface of the field. They spread out as far as possible, so you have no electric field inside the conductor, and instead it only exists outside. The other thing to note is if we have a circular sphere and that is creating a field, you could have lines of equal values for the electric fields, and those would be concentric circles. Anywhere along the outside of those values, you'd have equal electric fields. If you did have an irregularly shaped object, maybe it was teardrop shaped or something like that, you would have all of the charges accumulate near the sharper points, so you would have a value that is a little stronger at that point than where it's spread out or more uniform. Typically for an introductory physics course, we stick to the ideal situations, either a single point source, two unlike point sources that are spherical in nature, two like sources that are spherical, or two parallel plates where the field is uniform in between. Now, since we don't have an electric field inside of metal conductors, that can be used in everyday life. Computers have towers around them, and they're usually made of a metal frame, and that can reduce the amount of static electricity that's built up. That would avoid breaking the or overcharging the internal components of the computer. Also, the CPU itself is usually encased in a metal conductor box. It's almost like a little box that's inside, and that protects the CPU from any additional charge that may get past the metal frame itself. It would protect from overloading of the circuit. Coaxial cable uses this principle as well. It's a number, the center is a metallic cable typically made of copper, and then outside of that is a insulator, usually plastic. But around the plastic is usually a braided wire, and that braided wire acts as a metal conductor, so the signal itself is inside in that center wire, and it's protected from any electrical interference. So a coaxial cable will have that setup where you have a wire and then an insulator and then another metal braided wire and then another insulator to protect the integrity of the signal inside the wire itself. Other devices such as gaming systems or televisions or DVD players or Blu-ray players, they're going to produce electrical interference, and you don't want to affect the signal that's going into the television. So coaxial cable utilizes this principle to avoid signal interference. Once again, I mentioned earlier in this unit that the car frame is built with this principle in mind. The metal frame of the car protects passengers from static electricity. If a lightning bolt were to strike the car and your arms were inside the vehicle, you should be safe from the lightning strike. Consequently, more likely would be if you got in an accident and a power line fell into the car, you would also be safe from the electrical current because it would travel along the outer surface of the frame and then protect, inside the vehicle, the people are protected. If you were to try to open the door, stick your arm out the window, that could be when you got electrocuted. So if you ever get caught in a car and the power line's on the car, stay inside the vehicle. I know it's not going to be easy to stay calm in that situation, but try to remain calm and just stay in the vehicle. I would even lift my feet up and kind of sit in a lotus position so that you can avoid touching anything on the outside of the vehicle itself. So basically at this point, the electric field is defined as the region around a charged object where other charges will interact. We could solve for it mathematically or graphically, and we have a number of different ways that we can approach any problems that we're dealing with when looking at electric fields. At this point, I'll probably take the whiteboard out and show you some sample problems of electric fields that we can draw, and just give some examples of what it would look like, where the strong areas are and the weak areas are in the field. But a visual representation can speed our problem solving up considerably. Thank you. Okay, when we're drawing electric fields, we always look at WWPD, what would a proton do? And we draw field lines. And those are going to represent what the proton would do if placed in the field. So if you have a single source and it's negative, then anywhere you place a proton, it's going to be pulled inward. And basically this would show something that looks like this. Very similar to what it would look like if you had a gravitational field around the Earth. Proton placed here will be pulled in. Proton placed here will be pulled in. Wherever the proton's placed, it will be pulled towards the center, in this case towards the negative source. When you have two unlike sources, the general shape is that if you place a proton in the middle, it will be pushed straight across. If you place it off to the edge, it's almost a parabolic shape, like this. And as we go further away, they wrap around towards the other object. Now I could draw that, I have plenty of room here. But typically we'll run out of room on our papers. If we're drawing it by hand, we may find that it looks something like this, and this might be the edge of the page where it says lines. Now, we always have the lines going from positive to negative, so you have to make sure that you denote the direction as well. So if I were to place a proton in this vicinity right here, what would happen is it would be pushed directly in this way, in this manner, and then as it moves, it would curve back towards this other point, almost as if it were a projectile near the Earth's surface, and that negative would be pulling it towards it as this positive pushes it away. Now, no matter where I put an object, if it were negative, all that would happen is that it would move opposite the field lines. So the field lines point in the direction a proton would move, an electron would move in the opposite direction. So that's a single point source and two unlike sources. We'll look at the other two in a moment. Now, we could also have two similar sources. So I'm going to draw two negatives. And what they're going to do is if I place a proton anywhere near it, they're going to fight over it. So it almost looks like a spider. I think of this as a spider type shape. It looks something like that. Now in the center, if they're equal in strength, we have an asymptote. So this is a line of demarcation between the two where neither one would win the battle. Now a proton would be pulled in to these negative charges. So it looks something like this, inward arrows. If one were stronger, it would push the asymptote toward the weaker one. Now finally, we have our parallel plates, which might be the worst drawn parallel plates in the history of parallel plates, but here's our positive, here's our negative. And what's important about these is that they are equidistant and parallel in terms of the field lines, also the plates. So anywhere in the center, we have a uniform field. The edge, we have a little bit of curvature, and that's a fringe effect. And that works very similar to the point sources that were unlike. But anywhere in here, uniform electric field. So if we're going to do experiments in the lab, we're going to want to use parallel plates in order to do so. So those are the four different types of typical electric fields. We have the single point source, unlike point source, two like charges, and then the parallel plate. And those are our four main categories of different charges.